Here's a patient-specific aorta meshed for a blood flow simulation. Flow enters at the root, driven by the heart. But at each outlet, you have to prescribe a boundary condition. What pressure should the solver impose here? A zero-pressure, traction-free outlet is the easy choice, and it's wrong. It ignores the downstream vasculature, so the branch flow split and the pressure waveform both come out unphysical. The solution is a lump parameter model. Represent everything downstream of the outlet with 3 parameters. This is the full extent of the mesh, an inlet at the aortic root and 4 outlets. 3 are the arch branches feeding the head and arms. The 4th is the descending aorta. Physiologically, the circulation continues past each cut into arterioles and capillaries, far too many vessels to resolve directly. So we model their aggregate behavior. 2 effects dominate: resistance to flow and elastic storage of blood volume. The idea is old. Stephen Hales described it in the 1700s. Otto Frank formalized it in 1899. Windkessel is German for air chamber. A fire engine pump delivers sharp pulses. A trapped pocket of air buffers them into near-steady outflow. The aorta does the same. In systole, its elastic wall distends and stores part of the stroke volume. In diastole, elastic recall sustains flow after the valve closes. 2 quantities capture this: peripheral resistance and arterial compliance. The governing equation is identical to an electrical circuit. Pressure maps to voltage, flow to current, and resistance to a resistor. Compliance becomes a capacitor, charging in systole and discharging in diastole. A resistor and capacitor alone already reproduce the exponential diastolic decay, with time constant RC. But early systole is wrong. 2 elements can't match the aorta's input impedance at high frequency. A series characteristic impedance, ZC, corrects the upstroke. 3 elements, 1 differential equation relating pressure and flow, integrated alongside the 3D domain every time step. Each parameter has a distinct role. Resistance sets the mean arterial pressure. Compliance sets the pulse pressure. A stiffer, lower compliance aorta widens it, which is a hallmark of arterial aging. Characteristic impedance shapes the systolic upstroke. Tuned together, the 3 reproduce a measured patient waveform. In practice, each outlet carries its own Windkessel, tuned to that branch's share of cardiac output. At each time step, the solver computes the flow through every outlet face. The Windkessel returns the corresponding pressure, and that pressure is imposed back on the face. The 2 models advance together, beat after beat. The result is a physiological waveform: the systolic peak, the dichrotic notch at valve closure, and the diastolic runoff. 3 parameters per outlet, standing in for the entire distal circulation. 2 resistors and a capacitor, doing the work of an entire vascular bed. If you want the follow-ups, parameter tuning from clinical data, the 4-element model with blood inertance or fluid structure interaction when the wall deforms, let me know in the comments.